Logic, Tautologies, and Contradictions. Up to this point, we have looked at several logical connectives, including negation, conjunction, disjunction, exclusive or, implication, and biconditional. Now we are going to define two new things. Definition. A compound statement is a tautology if it is true for every possible combination of truth values of its component statements. Second definition. A compound statement is a contradiction if it is false for all possible combination of truth values of its component statements. Example. P and not P is a contradiction, and P or not P is a tautology. Looking at the truth table, we can see that this is true. We have P, which is either true or false. So not P is false when P is true, and true when P is false. When we OR two statements, P and not P, only one of them has to be true, so P or not P is true in both cases. That's a tautology. On the other hand, P and not P requires both parts, P and not P, to be true in order for their conjunction to be true. Well, P and not P always have opposite truth values, so they're never both true, they're always false. That is a contradiction. Example. Modus ponens is the term for a rule of inference that says if you know that P implies Q and you have P, then that implies Q. Consider the following statements. P, I study hard. Q, I will get an A on the exam. Thus, P implies Q for this example would be, if I study hard, then I will get an A on the exam, because P implies Q means if P, then Q. So, if we know that P implies Q is true, and P is true, that implies Q. So, it will be true that I will get an A on the exam. Truth table for modus ponens. Modus ponens written symbolically is P implies Q and P implies Q. We have two distinct simple statements, P and Q. We know there are four possible combinations, and in the first column for P we write true, true, false, false, and for Q we write true, false, true, false. P implies Q is where we start. That's the insidemost parentheses of the left-hand side of the expression. And P implies Q is true except when P is true and Q is false. Otherwise it's true. Any implication that starts with a false is always true. We will need to take that column, P implies Q, and have a conjunction of that with the column P. So we get P implies Q and P. Well, a conjunction is true when both parts are true, and the only place that happens is in the first row. Otherwise, we have at least one false, so our conjunction is false. Now we have the left side of the implication, and we also have Q, the right side of the implication. So we can find the truth values for the final implication. In the first row, we have true implies true, so that's true. And in all the other rows, the left side of the implication is false, which means the implication is true. Modus ponens is a tautology. It is always true, no matter what truth values the simple statements have. Truth table for modus tollens. Modus tollens says if we know P implies Q is true and we know not Q is true, then that applies not P is true. We can see this in a truth table. Again, we have two simple statements, so we start with the same set for P and Q. Inside the innermost parentheses on the left, we'll need P implies Q, and that's only false when true implies false. It's always true when P is false. We'll need not Q, and then we'll need the conjunction of the last two columns, and the only place that both of those are true is the last row, so we have a true there and false otherwise. Then for the right side we'll need not P. Those are the opposite truth values as P. And finally we can do the implication of the left side implies the right side, and we see in the first three rows the first part of that implication is false, so that's always true, and in the last row true implies true is always true. This is our second rule of inference. Modus ponens was our first. Example: is the following logical expression a tautology, a contradiction, or neither? Well, we have a complicated statement there that has three simple statements, P, Q, and R. With three simple statements, we need 2 to the third rows in our truth table, and we lay them out with the first column, P, being 4 truths and 4 falses. Q, we do 2 truths, 2 falses, 2 truths, 2 falses. And in the R, the third column, true, false, true, false, true, false, true, false. We need to start inside the left parentheses on the left with P or Q, a disjunction. A disjunction is only false when both simple expressions are false, and that's the last 2 rows. Now we need to work inside the other parentheses where innermost we have Q or R. Again, only false when both of the simple statements within it are false, and that's in the 4th and 8th row. But we don't need Q or R, we need not Q or R, so we reverse the truth values of Q or R, and now we're ready to take the conjunction of that with P or Q. That'll be true only when both parts are true, and that's only the 4th row. It's false otherwise. Now, does that whole thing imply R? Well, we have, except in one case, we start with a false, and that's always true. But if you look in the 4th row, we have true implies the value for R, which is false, and that's false. So this is not a tautology because the final column for the expression is not all trues, nor is it all falses, so this is not a contradiction. So the correct answer is it is neither a tautology nor a contradiction.